So this work indeed is a part of a project, a wider project, that concerns the study of additively manufacturing characteristics of the material, the relation between the characteristics, the mechanical characteristics, and the defects inside the material itself, the defects and the process parameters that have caused that defects. And in particular, we are studying this correlation by using the artificial intelligence. If you were here yesterday in the presentation of Professoressa Iacoviello, she spoke about something. She introduced she said some important information about the image analysis, so the analysis of the defects and the AI means. In particular, if you remember, she said that these means need to be trained with experimental data. And in this presentation, I will talk about the generation of this experimental data. Here we have the outline of this presentation. So first of all, I'm presenting the specimen that we have adopted, the geometry, the raw material, the powder that we have used, and the manufacturing parameters. That is the core of this project. Then we started. I will present the manufacturing process of this specimen. They were produced by EBM, and also the manufacturing of the specimen itself. So the plates that were produced by additive manufacturing were machined to obtain the final specimen. Then there is the presentation of the test layout, and finally the result. First of all, the specimen. The specimen is a classical specimen, the compact tension from the ASTM Ti6Al4V standard. This is our specimen presented a almost squared section with an edge of 50 millimeters. The notch had a width of 2.5 millimeters. The thickness of the specimen itself was 8 millimeters, and the distance between the tip of the notch and the line between the loading pin was 8 millimeters. As concerns the raw material, this is a powder bed process, and consequently, we used the powder. The metal considered was titanium alloy, that is the Ti6Al4V vanadium. That is an alloy commonly used for aerospace application. Here we can see micrographs of the powder, the raw powder. We can observe the shape of the particles that were spherical, almost perfect. The deformed particles were very few. We evaluated also the dimension of these particles, almost all the particles. The diameter of these particles was between 45 and 106 microns. And the sphericity and the uniformity of dimension are two important parameters to guarantee a good compaction of the powder during the process. As concerns the manufacturing parameters, we adopted 4 different sets that were called A, B, C, D. And the difference between these sets was in the speed of the electron beam and in the current of the same beam. As concerns other parameters, such as the H distance, the focus offset, the thickness, the layer thickness, the thickness of the powder layer, and the voltage of the beam, they were kept constant. By varying the speed and the current of the beam, we obtained 4 different levels of energy. Indeed, the levels were, we can consider 3 levels, because the parameter B and parameter C present an almost quite similar energy, even if they were obtained with totally different parameters that were almost twice the other. And this because we wanted analyze not only the effect of the energy, but also of the parameter itself. As concerned the process, as I said, we adopted the EBM, the electron beam melting. The machine used for producing the plates was the Arkham A2X, that is a commercial machine. The process is very similar to the most common selective laser melting. It consists in producing a bed of powder, a layer of powder, and then a beam. In this case, an electron beam. In the case of the laser, a laser beam, consists in melting, in selectively melting the particles where needed. Then the process went on by spreading another layer of powder, and so on. As concern the production, after the production of the plates, they were machined to produce the notch necessary for generating the crack, and the holes to connect the specimen to the machine. It was important noting that the specimen, the plates, were built with the main dimension parallel to the build direction. But we analyzed 2 situations. One with the crack growing in the horizontal direction, that is a direction perpendicular to the grow direction. The other case, the crack was vertical, that is parallel to the grow direction. Obviously, the plates were similar, but they were machined by simply rotating the holes and the notch. As concern the test, they were carried out by using a computer-assisted hydraulic machine, and to automate the process, because the duration of this test is quite high, several hours. And as concerned the test parameters, we considered a load ratio of 0.1, a load frequency of 30 Hz, and the tests were carried out at room temperature. The crack length was evaluated by adopting a compliance method. This means that we evaluated the opening of the edge, so the crack opening displacement, and then by using a double cantilever mount cage, and then by using some relation, we were able, some relation based on the stiffness of the material, we were able to calculate the length of the crack. Obviously, we validated this method, we controlled the results by using a traditional method based on the use of a microscope. Here we can see some micrographs of the specimen that were prepared through the traditional metallurgical techniques. The first specimen, that is the A, presents very few defects. We can see some only gas pores, very, very little. As concerns the specimen B, I want to remember that specimen A was produced with the highest level of energy. As concerns the specimen B, we can observe also some lack of fusion defects, and the gas pores were bigger. Specimen C, we can see more lack of fusion and more gas pores. Indeed, the specimen B and specimen C, by carrying out a more accurate analysis on more images, were quite similar. From a statistical point of view, I can say here that this is the best case and this is the worst case. Finally, for the specimen D, we can observe a lot of defects: lack of fusion, unmelted particles, gas pores. And lack of fusion is very dangerous as a defect because it is a sort of pre-crack. And if you have a lot of this pre-crack inside the material, you can break the specimen very, very easily. In fact, if we have a look at the Paris curves, so the crack growth rate, stress intensity factor range diagram, we can observe that the curve relevant to the D specimen is on the top left of this graph. So you need few energy to break this specimen. As concerns the other family, we can see that they are grouped more or less in the same zone. So the behavior is almost similar. This for the specimen with the horizontal crack. For the specimen with the vertical crack is more or less the same. We can observe that the specimen D is separated from the other specimen. I have also made a comparison between the A and the D specimen, vertical and horizontal crack, and we can observe that the curves tended to move towards the bottom and the right of the diagram, especially for the D specimen. This means that the resistance against the fatigue crack growth of the vertical crack was higher. But to understand better this phenomena, we carried out some analysis of the fracture surface. Here we can observe the fracture surfaces for the horizontal specimen, and we can see that, especially for the A specimen, we can observe a sort of transgranular fracture. In fact, in this type of material, the grains are elongated along the growth direction. This is a particularity of this process. And instead, for the case D, we can observe a big defect, a lack of fusion defect, also unmelted particles, and this explains the low resistance of this specimen. As concerns the vertical crack, in this case, we have that the cracks moves along the boundary, the green boundary between two grains. But we can notate also another thing. There are a lot of several secondary cracks here, and here. In this case, is more evident. And especially for this case, we can observe that the distance between these secondary cracks is equal to the layer thickness. So we can conclude that the bonding between layers was not so good, especially for the D specimen. In fact, this is another micrographs taken at lower magnification, and we can observe that this specimen presents a sort of skin, of outer skin, that presented a different morphology from the, let's call this zone from the core. Here we can see a lot of lack of fusion, unmelted particles. Here the material is better. The material is continuous. So, in conclusion, we can remember that I have analyzed the effect of the process parameter on the fatigue crack growth rate. The specimen printed with low energy presented more defects and consequently low resistance. We observed, especially for this specimen, a sort of anisotropy. In fact, if you remember, the curves of the specimen D with the horizontal crack were worse than that with the vertical one. However, we have to further investigate the effect of the defect position and shape on the fatigue crack growth. I want to thank you, the Italian Ministry of University and Education that financed this project, and also you, the audience.